All right, let's just jump right in. When I say the word entropy, what pops into your head? For a lot of us, right, it's this idea of decay, a universal law that says everything is just doomed to fall apart. But what if I told you that's not the whole picture? Not even close. Today, we are going to bust the biggest myth about entropy. I mean, it's a huge question, right? Kind of philosophical. Is everything in the entire universe, you, me, the stars, just on this one-way street to complete chaos and ruin? It's a pretty depressing thought, isn't it? And for more than 100 years, the standard scientific answer has basically been, yep, pretty much. And here's the supposed culprit, the famous second law of thermodynamics. Now, this is a huge deal in physics, one of the most fundamental rules out there, and it basically says that in a closed-off system, entropy, or disorder, always increases. It's what they call the arrow of time, pointing from a nice, neat beginning to a messy, chaotic end. But that's the very idea we're going to poke some holes in today.
Okay, so before we can properly bust this myth, we've got to understand where it comes from. So let's do a quick and dirty breakdown of what classical entropy actually is and why we always connect it with this idea of everything falling apart.
So here's the key thing to get. Classical entropy isn't just disorder. That's a bit of a simplification. It's really about how energy is spread out, how it's distributed in a system. You can see in this formula that entropy, that's the S, is tied to temperature, the T. To put it really simply, as you pump in heat and the temperature rises, you're basically giving that energy more ways to arrange itself. And that explosion of possibilities, that's what we call an increase in entropy. And this graph, right here, is a perfect picture of that second law in action. See how as you add more heat, moving along the bottom, the entropy just keeps climbing? It's showing us, plain and simple, that the more energy you stuff into a system, the more that energy wants to spread out, get messy, and, you guessed it, increase the system's entropy. Here's a perfect everyday example. Just picture an ice cube melting in a glass of water. The heat from the water, which is more concentrated, naturally flows into the colder ice cube. It spreads out, right? It melts the ice until everything is the same temperature. That natural tendency for energy to go from a hot, concentrated spot to a cold, spread-out state, that is the absolute engine of entropy. Okay, so we've laid down the law, so to speak. Entropy always goes up. Everything gets more disordered. But this is where the story takes a massive plot twist, because now we're going to look at the exceptions. And trust me, these are the cases that change everything we thought we knew. So this brings us to the big, script-flipping question. Is this rule, this law of decay, really, truly universal? I mean, are there no exceptions? Could there actually be situations where nature does the opposite, where it builds things up, creates order from chaos, and actually makes entropy go down? And here it is. This is the secret. The second law, the one we all learn about, really only applies to systems where particles are pushing each other apart. Think about a gas, right? Molecules bouncing around, spreading out. Those are repulsive forces. And yeah, they make energy disperse. But what about the opposite? What about systems dominated by attractive forces, like gravity? Well, there, the exact opposite happens. Particles get pulled together, which concentrates energy and actually creates order. And believe me, this isn't just some abstract idea. We can actually see it happening, from the cosmic scale all the way down to here on Earth. I mean, think about a black hole. It's literally sucking in energy and matter from the vast cold emptiness of space, concentrating it. Or gravity. It pulls together these giant messy clouds of gas to form incredibly ordered structures like stars and entire galaxies. Even something as simple as water freezing. When supercooled water suddenly snaps into a crystal, it releases heat and forms this perfectly ordered structure. That is a state of lower entropy. Yeah, and this quote from Jerry Z. Liu just hits the nail on the head. He says, "The commonly assumed dispersive tendency of energy is not universal, but rather a characteristic of small systems dominated by repulsive interactions." What he's saying is, this idea that energy always spreads out, it's just not a universal law. It's a special case, a behavior you see when things are pushing each other apart. The universe, it turns out, is way more interesting than that. So, okay, if the universe isn't just on a one-way trip to decay, then what in the world is it doing? This shift in thinking opens up a whole new perspective on the cosmos, one that's a lot more dynamic and, frankly, a lot more exciting. So how do we square this circle? Well,
It turns out that part of the confusion comes down to the fact that we're often talking about two different kinds of entropy without realizing it. There's the classical one we started with, which is all about how a system's energy is spread out on a big scale. But then there's statistical entropy, which is about how the tiny little components of a system are arranged. And here's the kicker. Just because you're concentrating energy, that doesn't automatically mean the individual parts are getting messier. And in fact, get this. These two definitions can literally contradict each other. Under certain conditions, like when you get really, really close to absolute zero, one definition might say entropy is going up, while the other says it's going down. That just goes to show you that they're describing two very different things, and you can't just swap one for the other.
So what's the big takeaway here? It's that the story of our universe is not just a simple story of decay. It's not about everything just falling apart. It's this incredible, epic tale of constant transformation. You have attractive forces like gravity building these amazing complex structures, while at the same time, repulsive forces are working to spread energy out. It's like this cosmic dance between creation and dispersion happening all the time. And that leaves us with a final thought. And honestly, it's a much more hopeful one. So is the story of our universe really just about decay, a slow, boring fade into nothing? Or is it something more, an endless transformation where energy is constantly reshaping itself, creating new and beautiful complexity? The evidence, it seems, is pointing to a universe that is far more dynamic than we ever gave it credit for. So, what do you think?